400 years. That is how long the Great Red Spot has been visible from Earth, longer than the United States has existed, and longer than most modern nations have been on the map. But this is not simply a giant storm. Its winds reach roughly 640 kilometers per hour, about 400 miles per hour, sustained across a system that has persisted for centuries. The storm itself is wider than Earth, yet scientists still debate exactly how to classify something with no true equivalent on our planet. For generations, astronomers assumed they understood what they were seeing: a giant storm, a permanent feature, a strange red oval. Then Juno arrived. In 2017, NASA's spacecraft began making close passes over Jupiter, carrying instruments capable of probing beneath the visible cloud tops. For the first time, scientists could begin measuring how deep the Great Red Spot actually extends and how its enormous circulation connects to the atmosphere below. The results challenged the picture that had survived for centuries. The storm reaches far deeper than expected, extending hundreds of kilometers beneath the visible clouds, while its structure changes dramatically with depth. And there is another problem. The Great Red Spot is shrinking. Astronomers have tracked its changing size for decades, and the storm that once appeared enormous enough to dominate Jupiter's entire appearance is becoming smaller. Why? What keeps a storm this enormous alive for centuries? What did Juno actually find beneath those red clouds? And if the Great Red Spot is slowly disappearing, what does its changing structure reveal about the atmosphere of the largest planet in our solar system? We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. The story begins with the storm that has been watching humanity for 400 years. Long before spacecraft crossed the darkness between worlds, Jupiter was already part of humanity's record of the sky. Babylonian astronomers tracked its movement as early as the 7th century before Christ, treating its wandering among the stars as something worth measuring and remembering. Centuries later, that patient observation became something more powerful when Galileo Galilei turned a telescope toward Jupiter in 1610. Within days, Galileo saw 4 points of light moving around the planet. They were moons, now known as Io, Europa, Ganymede, and Callisto. Their motion provided direct evidence that Earth was not the center of every orbit. For us, it was an early glimpse of a larger principle. Jupiter could become a laboratory for testing ideas about how worlds move. The Great Red Spot entered that record much later. Giovanni Cassini may have observed a large storm in 1665, although scientists cannot establish that it was the same feature we see today. The first secure record of the present storm dates to 1831. Between those observations lies a remarkable uncertainty, because Jupiter keeps no convenient geological archive on its surface. At 88,846 miles across, Jupiter is enormous enough to contain roughly 1,300 Earths by volume. Yet there is nowhere to stand. Its visible atmosphere gradually thickens and compresses downward, with pressure and temperature changing continuously as hydrogen and other gases become increasingly dense. What looks like a surface from a telescope is only the upper boundary of a much deeper planetary system. Then there is the rotation. Jupiter completes a day in just under 10 hours, an extraordinary pace for a world of such size. That rapid spin organizes its atmosphere into broad bands, where powerful jet streams race in opposite directions and maintain the striped pattern visible from Earth. The Great Red Spot is embedded within this moving architecture, occupying the southern portion of Jupiter's banded atmosphere. Its position is constrained by neighboring flows traveling in opposite directions, giving the storm a setting unlike anything we encounter on Earth. For centuries, though, that setting remained something we could only watch from afar. At the most favorable alignments, Jupiter comes within roughly 365 million miles of Earth, yet even that distance leaves the deeper planet concealed. Through a telescope, we could follow the storm's changing outline and shifting color. We could watch it rotate across the Jovian disk. But beneath those clouds, the structure remained inaccessible, and every visible detail ended at the same boundary. The planet showed us its weather while keeping its depths beyond the reach of observation. Even the storm's apparent permanence offered little guidance about what sustained it, because a visible shape reveals almost nothing about the forces moving beneath it. Imagine Jupiter's storm as a shape changing while you watch it. Across the centuries, its proportions have never stayed perfectly fixed. In the late 19th century, observers estimated the Great Red Spot at roughly 25,000 miles across. That enormous oval could have held three Earths side by side. Today, the scale has changed dramatically. Measurements place the storm near 10,000 miles wide, still larger than Earth's 7,917-mile diameter. The difference is more than a matter of appearance. As the vortex contracts, its outline has become increasingly circular, changing the geometry of a system that once stretched much farther across Jupiter's atmosphere. Size alone, however, tells us very little about motion. The storm turns counterclockwise in Jupiter's southern hemisphere, while different regions move at different speeds. Near the outer boundary, winds exceed 400 miles per hour. Deeper toward the central region, the circulation slows considerably, producing a striking contrast between the racing perimeter and the more stable interior. You can think of the difference as layers of motion occupying the same space. The outer winds sweep around the vortex, while the center resists those changes, preserving its own pattern. Even on a world without a solid surface, the storm maintains recognizable internal organization. Its vertical scale adds another dimension. The upper clouds rise roughly 5 miles above the surrounding cloud deck, giving the vortex a raised profile as well as its immense width. From above, we see an oval. From the side, we would see something more like a broad atmospheric mound, shaped by gases moving upward and outward. Then there is the color that gave the storm its name. The deep reddish tones have changed over time, ranging from pale shades to much darker reds. Scientists have proposed several chemical explanations, including compounds involving sulfur, phosphorus, and complex carbon based material. One leading explanation focuses on chemistry high in the clouds. Sunlight can break apart ammonia ice, initiating reactions that create reddish compounds known as chromophores. These molecules absorb particular wavelengths of light, altering the color we see from distant telescopes. Yet the visible color represents only the uppermost chemistry we can observe directly. The deeper atmosphere may contain different compounds, different temperatures, and different chemical pathways. As we look farther down, the connection between the storm's appearance and its underlying chemistry becomes increasingly uncertain. That uncertainty matters because the red spot's color is only the surface expression of a structure extending far beneath it. What looks like one enormous red shape from Earth may contain several chemical environments stacked through its depth, each responding differently to sunlight, pressure, temperature, and the movement of material within the vortex. Even its apparent simplicity becomes difficult to preserve once we consider how many layers are moving at once. From our distant viewpoint, scale hides that complexity rather than revealing it. A spacecraft built for Jupiter had to survive a planet that does not forgive mistakes. Juno launched on August 5th, 2011, beginning a journey of roughly 1.74 billion miles toward the largest world in our solar system. Nearly 5 years later, on July 4th, 2016, it entered orbit around Jupiter. Its mission required a different kind of vision. Ordinary cameras could study the cloud tops, but they could not see through them. Juno carried a microwave radiometer, an instrument that detects thermal energy emerging from deep within the atmosphere. By reading how microwaves changed across different frequencies, scientists could infer temperature and chemical composition beneath the visible clouds. Getting close enough was another challenge. Juno follows a highly elongated orbit, spending most of its time far from Jupiter before plunging inward at tremendous speed. During its closest passes, the spacecraft comes within roughly 2,600 miles of the cloud tops. No previous spacecraft had repeatedly ventured so close. That proximity places Juno inside one of the harshest radiation environments surrounding any planet. Jupiter's magnetic field traps enormous populations of energetic particles which can damage electronic components and corrupt scientific measurements. Engineers placed Juno's most sensitive electronics inside a titanium radiation vault, using the dense metal as a protective barrier. Then came July 11th, 2017. Juno was making its sixth close approach to Jupiter, and its flight path carried it directly across the Great Red Spot. For a few minutes, the spacecraft passed above the storm at close range. Every instrument capable of contributing data was operating. Cameras recorded the visible structure, while other sensors measured magnetic fields, gravity, particles, and atmospheric properties. The microwave radiometer was doing something especially important. Its antennas were receiving microwave emissions from beneath the cloud tops, allowing scientists to distinguish structures at different depths. Instead of seeing only the storm's upper appearance, they could begin separating its hidden layers. The observations were designed to test decades of atmospheric theory. Before Juno arrived, many models treated the Great Red Spot as a relatively shallow feature, perhaps extending only 60 to 120 miles downward. The storm was understood primarily through what telescopes could observe from above. Now, for the first time, we had measurements coming from beneath that boundary. 6 microwave channels examined different levels of the atmosphere simultaneously. Each channel responded differently to the material below, creating a layered picture from signals that had traveled upward through the storm. The data did not resemble a simple, shallow vortex. Deeper signals continued to show the storm's influence, revealing that its circulation extended far beneath the region visible from Earth. For scientists, the significance was larger than a new measurement. A spacecraft had finally transformed the Great Red Spot from an image into a three-dimensional atmospheric problem, giving us access to information that generations of observers could never obtain from the cloud tops alone. The storm could now be studied as a structure with depth, layers, and hidden motion, rather than simply as a red shape turning across Jupiter's face. The first clue was hidden in the microwave measurements, where the storm's influence continued long after its visible clouds had ended. Juno's instruments traced the vortex downward through Jupiter's atmosphere, revealing a structure far deeper than earlier models had allowed. The Great Red Spot reaches roughly 300 miles beneath the cloud tops. That depth is difficult to picture from Earth, so consider the Mariana Trench, the deepest known point on our planet. At about 7 miles deep, it would occupy only a small fraction of the storm's vertical reach. Pressure changes everything down there. Around 300 miles below the clouds, the atmosphere experiences pressures roughly 100 times greater than those at Earth's sea level. Hydrogen becomes increasingly compressed and the familiar distinction between gas and liquid begins to lose its usefulness. Jupiter has no sharp atmospheric floor. Instead, material becomes denser continuously as gravity pulls it downward, transforming the character of the hydrogen along the way. What begins high above as a thin atmosphere gradually becomes something far more compressed, with no simple boundary separating one state from another. That matters for the Great Red Spot because its circulation is connected to this deeper environment. The storm is woven into Jupiter's atmosphere rather than floating above it like a separate object. Its enormous vortex reaches downward into regions where pressure, density, and motion differ radically from conditions near the visible clouds. For decades, atmospheric models had treated the storm as comparatively shallow. Those models were built from the evidence available at the time, because telescopes could measure movement and temperature only near the upper atmosphere. Juno changed the problem by measuring signals that carried information from beneath those visible layers. The discovery forced scientists to reconsider how the storm could maintain its circulation. A vortex extending hundreds of miles downward has access to a much larger volume of atmosphere than previously assumed. Deep motion can also connect the storm with energy and material moving through Jupiter's interior. You can imagine the difference between tracing a shape on paper and discovering that the shape continues through an entire stack of layers beneath it. The visible red spot had seemed complete from above, yet its measured structure reached much farther into the planet. There was another consequence. The deeper Juno looked, the less useful it became to describe Jupiter's atmosphere as a thin shell surrounding a planet. The atmosphere itself forms a vast, moving part of Jupiter, extending downward through increasing pressure and density. At 300 miles, Juno had mapped the storm's measured route. Beneath that depth, its microwave observations could no longer provide the same level of direct detail. The boundary of knowledge had moved downward, but it had not disappeared. What we found then was a storm whose visible dimensions conceal an immense vertical structure. Its red clouds are only the upper expression of circulation, extending hundreds of miles into a world where ordinary ideas about weather, gas, and depth begin to change. A storm on Earth eventually runs out of fuel. Hurricanes draw their energy from warm ocean water, weakening when they encounter cooler surfaces or land. Jupiter offers no such boundary. There is no ocean beneath the Great Red Spot, no coastline, and no solid ground where friction can rapidly drain its circulation. Instead, Jupiter itself supplies heat from within. The planet releases roughly 1.7 times more energy into space than it receives from sunlight. That excess comes partly from the slow compression of Jupiter under its own gravity. As the enormous planet contracts, gravitational energy is converted into heat, a process known as Kelvin-Helmholtz contraction. Deep inside the atmosphere, that heat does not simply remain trapped. It moves upward through convection, the circulation created when warmer material rises and cooler material sinks. These vertical movements carry energy through layers far beneath the visible clouds, linking the upper atmosphere with deeper regions of the planet. For the Great Red Spot, that connection may be crucial. Its deep roots place the storm within the same broad environment where internal heat is transported upward. Instead of depending entirely on conditions near the cloud tops, the vortex may draw energy from a much larger atmospheric volume beneath it. Yet energy alone cannot explain its remarkable persistence. A storm needs boundaries that help organize its motion. Around the Great Red Spot, powerful jet streams travel in opposite directions, above and below the vortex. Their opposing flows help confine the storm to a narrow range of latitude, limiting the paths through which it can wander. The result is an unusual arrangement. Heat rises from below, circulation carries that energy upward, and neighboring jet streams help contain the vortex laterally. With no solid surface beneath the atmosphere, there is also no ordinary ground friction acting directly against the storm. You can see why Jupiter allows a weather system to persist for generations. Its atmosphere supplies energy from within, while its rotation organizes that energy into enormous, long lived structures. The red spot exists inside a planetary machine that continually moves heat, gas, and momentum through its depths. But efficiency has limits. The storm still loses energy through interactions with surrounding flows, smaller vortices, and turbulence along its outer boundary. Those losses are measurable, and observations show that the balance has been changing. Small differences, repeated across immense distances, can gradually reshape a storm whose lifetime spans centuries. That distinction matters. Jupiter can sustain the Great Red Spot for centuries without making it permanent. Its energy supply may remain vast, while the storm itself gradually becomes less efficient at retaining what it receives. The same atmosphere that helps preserve the vortex can also provide pathways for its energy to escape. The Great Red Spot becomes stranger when we stop viewing it as one object. Juno's measurements reveal a hierarchy of motion, with different regions turning at different speeds and responding differently to forces around them. At the outer edge, the circulation reaches its greatest speeds. Winds there can approach 400 miles per hour, sweeping around the perimeter while maintaining the storm's enormous rotation. Farther inward, the behavior changes. The central region moves more slowly. Its rotation is remarkably stable, creating a sharp contrast with the faster material surrounding it. From our distant viewpoint, the entire storm appears to rotate together, yet its interior contains separate zones with their own patterns of motion. Between those regions lies a transition zone. Here, velocity changes rapidly across relatively short distances, producing strong shear, which occurs when neighboring layers move at different speeds. Turbulence becomes more pronounced in this region, allowing energy and momentum to move between the faster outer circulation and the slower interior. The vertical structure adds another layer of complexity. The upper clouds above the storm are colder than the surrounding atmosphere, forming a broad region of reduced temperature over the vortex. Scientists have observed this thermal difference in infrared measurements, suggesting that the storm's circulation influences conditions well above its main visible structure. That colder region is especially interesting because rising gases expand as pressure decreases, causing them to cool. The Great Red Spot's enormous circulation can therefore alter temperatures at higher altitudes, linking motions deep inside the storm with conditions far above the clouds. Then Juno revealed that the vortex contains smaller vortices of its own. These secondary eddies rotate within the larger circulation, with some moving in the opposite direction. Instead of a single enormous flow, we are looking at a nested system where smaller structures interact with the dominant vortex. Their role remains under investigation. One possibility is that these smaller vortices help redistribute energy within the storm, moving momentum between different regions and allowing some energy to escape from the main circulation. Their interactions may therefore influence how the Great Red Spot changes over time. Microwave observations provide another clue. At certain wavelengths, deeper portions of the storm appear darker than corresponding regions near the upper clouds. Because microwaves respond differently to atmospheric materials at different depths, these variations can reveal changes in composition that ordinary images cannot show. The result is a storm with chemical layers as well as moving layers. Material found near the cloud tops does not necessarily have the same distribution deeper below, and the circulation can transport compounds between regions while pressure and temperature alter their behavior. When you trace all these differences together, the red spot begins to resemble a layered atmospheric structure rather than a single rotating mass. Its outer winds, central circulation, transition zone, thermal envelope, and embedded vortices interact continuously. Each part contributes to the behavior of the whole, while none can fully describe the storm by itself. The Great Red Spot has never been exactly the same shade of red. Across decades of observation, astronomers have watched it fade toward pale pink, turn orange, and deepen into a darker brick red approaching brown. Its changing color sometimes follows changes in size, although the relationship is inconsistent enough to resist a simple explanation. Color, here, is chemistry made visible. The leading explanation involves chromophores, compounds that absorb certain wavelengths of sunlight and reflect others back towards space. In the upper clouds, sunlight interacts with ammonia ice and triggers chemical reactions that can create these reddish materials. That explanation works reasonably well near the top. Juno revealed that the deeper storm is much more complicated. Microwave measurements detected differences with depth, showing that the materials responsible for the storm's appearance are not evenly distributed throughout its enormous vertical structure. At 50 miles below the visible clouds, the chemistry can differ from conditions 200 miles deeper. By 300 miles, we are examining an environment where pressure and temperature have changed substantially. The result is a storm with multiple chemical layers. Material can rise, sink, mix, and react as atmospheric currents carry it through different conditions. What begins as one substance at depth may be altered before reaching sunlight near the upper clouds. One possibility involves phosphine, a gas that can originate in Jupiter's deeper atmosphere. If material containing phosphine is transported upward, sunlight can drive reactions involving phosphorus and produce compounds with reddish characteristics. The idea remains under investigation because the precise chemical pathway has not been demonstrated throughout the storm. Another possibility involves sulfur. Compounds containing sulfur may originate much deeper within Jupiter and become transported upward through the red spot's circulation. Once exposed to different pressures, temperatures, and sunlight levels, those compounds could contribute to the changing colors observed from Earth. There may be more than one process operating at once. Jupiter's atmosphere contains many chemical ingredients, and the Great Red Spot provides an enormous vertical circulation system capable of moving them through very different environments. Yet there is a fundamental limit to what Juno could determine. The spacecraft measured the atmosphere remotely. It did not collect a physical sample from 300 miles down and bring that material back for laboratory analysis. We have attempted direct sampling before. On December 7th, 1995, the Galileo atmospheric probe entered Jupiter and transmitted measurements while descending through the clouds. It survived for about 57 minutes before pressure and heat ended its mission. The probe reached roughly 95 miles below the cloud tops. That sounds immense until we place it beside the red spot's deeper structure. It sampled only a portion of the atmosphere, far above the storm's deepest measured reach. So the chemistry beneath the red clouds remains partly inferred. We can detect signals, compare wavelengths, and model reactions, but the deepest materials have never been physically sampled. The color we see from Earth may therefore be the visible consequence of chemistry unfolding across hundreds of miles, with each layer contributing something different to the appearance of the storm. The Great Red Spot has been changing shape for generations, and the record is now long enough to show that the change is measurable. 19th century observers estimated the storm at roughly 25,000 miles across, giving us the earliest useful scale for its enormous reach. By the time Voyager encountered Jupiter in 1979, the measured width had fallen to about 15,500 miles. Hubble Space Telescope observations in 1995 placed it near 13,000 miles. Each measurement captured a different moment, and together they trace a gradual contraction across more than a century. Then the decline became harder to dismiss as ordinary variation. By 2014, the storm had dropped below 10,000 miles across for the first time in the modern record. Current estimates place it near 10,000 miles, meaning the vortex has lost more than half its width since the largest 19th century measurements. The pace has changed too. Between 2012 and 2014, observations indicated a loss of roughly 580 miles in width each year. That interval drew particular attention because the contraction appeared faster than the long-term trend suggested. Size, however, is only one part of the story. As the Great Red Spot contracts horizontally, its outline has become less elongated. The old oval is gradually becoming more circular, changing the proportions of the vortex while its internal circulation continues. Something else is happening vertically. Measurements suggest the storm has become taller as its width decreases, concentrating its circulation into a smaller horizontal area. The result is a vortex whose changing dimensions cannot be described by simple shrinkage alone. Imagine taking a broad spinning pattern and compressing its footprint while preserving much of its vertical structure. The circulation becomes increasingly concentrated, and the relationship between width, height, and rotational energy becomes more important. That change has opened a difficult question for planetary scientists. A smaller storm can sometimes become more compact and dynamically concentrated without immediately losing its coherence. The red spot's increasing vertical extent could therefore reflect a reorganization of its circulation rather than simple weakening. Yet the long record also shows that something fundamental has changed. The storm is no longer following the dimensions recorded by observers in earlier centuries, and its contraction has occurred across multiple generations of measurement. For us, the value of this history lies in its continuity. Voyager, Hubble Space Telescope observations, modern ground-based telescopes, and long-running observations by astronomers have each added another point to the record. No single image reveals the trend. The trend emerges only when those measurements are placed together across time. The Great Red Spot therefore gives us something rare in planetary science, a centuries-long experiment conducted by the atmosphere itself. Its changing width, shape, and vertical structure allows scientists to watch a planetary system evolve, one measurement at a time. A storm can lose strength without losing its identity, and the Great Red Spot may be doing exactly that. Scientists have several competing explanations for its contraction, yet none accounts for every observation. One leading idea involves the smaller vortices moving through Jupiter's cloud bands. These storms frequently encounter the Great Red Spot, where some become absorbed into its circulation. In earlier decades, such encounters may have supplied additional momentum and energy, helping the larger vortex maintain itself. Recent observations suggest a different outcome. Some smaller vortices are disrupted as they approach the red spot, losing their organized rotation before they can become useful additions. The larger storm still consumes them, but the exchange may no longer provide enough energy to offset what escapes from its boundaries. Another possibility involves the jet streams surrounding the vortex. These powerful atmospheric currents help constrain the storm's position, but their strength and latitude can change. Even modest shifts could alter how efficiently they contain the circulation, allowing energy and momentum to leak into neighboring regions. Deep beneath the clouds, another process may matter. Jupiter's internal heat drives convection, with warmer material rising through the atmosphere. If those deep convective patterns shift in location or intensity, the red spot could receive a different supply of energy from below. There is also a more fundamental possibility. Perhaps the storm has always been slowly decaying, while its enormous size simply made that decline difficult to recognize. A system can persist for centuries and still be moving toward an eventual end state. For us, the difficulty lies in separating these effects. Jupiter's atmosphere is constantly producing storms, absorbing vortices, shifting jet streams, and transporting heat through immense depths. Each process can influence the others, making it difficult to isolate one cause from the rest. Computer models can reproduce parts of the observed behavior, but the complete history remains harder to explain. The timing of the contraction matters, as does its changing rate, shape, and vertical structure. A theory that explains one feature may struggle with another. That leaves planetary scientists with a picture built from several interacting possibilities. Feeder vortices may have become less effective. Jet streams may have changed. Deep convection may have shifted. Long-term decay may have been underway all along. The most useful explanation may therefore involve several processes acting together. Each one changes the conditions experienced by the others, so the storm cannot be understood as an isolated engine operating independently of its surroundings. What remains especially difficult is the speed of the change. The storm is contracting faster than many earlier models anticipated, showing that Jupiter's atmosphere still contains processes we have not fully captured in our equations. Along the Great Red Spot's outer edge, the boundary itself has begun to change. Since around 2019, astronomers have repeatedly observed elongated streamers peeling away from the storm and stretching into the surrounding atmosphere. At first glance, these events look almost like pieces being torn from the vortex. They are sometimes described as flakes, but the material involved is not solid. Each streamer is a region of organized atmospheric rotation that has lost its coherence near the storm's perimeter. Once detached, these structures are carried away by neighboring jet streams. The surrounding atmosphere absorbs them, dispersing their motion into the broader circulation. What disappears is therefore more than a visible streak. Some of the storm's organized rotational energy leaves with it. The timing has made these events especially interesting. Earlier observations recorded occasional disruptions along the red spot's boundary, but since 2019, the phenomenon has appeared more frequently and with greater regularity. You can think of the edge as a constantly changing interface. Inside it, the storm maintains a coherent circulation. Outside it, powerful atmospheric currents move independently. Where those systems meet, differences in speed can create shear, stretching portions of the vortex until they can no longer remain attached. Each event, therefore, provides scientists with a way to measure how the storm is interacting with its surroundings. The frequency, size, and behavior of these detached streamers can be compared across months and years, creating another record of the red spot's changing condition. But an important distinction remains unresolved. Does flaking actively accelerate the storm's shrinkage, or does a shrinking storm simply become more vulnerable to flaking? The difference matters. If the streamers are removing significant rotational energy, they could be contributing directly to the contraction. If they are mainly a consequence of changes already occurring within the vortex, then the flaking would be an indicator rather than a primary cause. Researchers are also considering a more unexpected possibility. Some models suggest that shedding material could help stabilize the storm by releasing excess energy from its outer regions. In that interpretation, the flakes would function somewhat like a pressure release mechanism, allowing the vortex to adjust without undergoing a much more disruptive breakdown. That idea remains a minority interpretation. The observations are still too limited to establish exactly how the process affects the storm's long term evolution. For now, every detached streamer becomes another measurable event in the red spot's history. Ground based observatories and the Hubble Space Telescope can track these changes repeatedly, allowing astronomers to build a record that a single spacecraft encounter could never provide. The pattern is becoming increasingly important. As the storm changes, scientists can count how often its edges shed organized structures, examine where those structures form, and compare their behavior with changes in the vortex itself. The red spot is therefore losing pieces of its organized circulation in a process that can now be watched almost as it happens. Whether those losses are driving the contraction or revealing a deeper transformation remains one of the central uncertainties in understanding the storm's changing boundary. The disappearance of the Great Red Spot would change more than one feature on Jupiter. Its removal could alter the circulation around an entire region of the planet, leaving scientists to watch a system reorganize without knowing exactly what form it would take. The storm occupies a strategic position between powerful atmospheric currents. For centuries, its circulation has interacted with those jet streams, exchanging momentum and energy across the surrounding cloud bands. Remove that circulation, and the balance could shift. Computer models suggest several possibilities. New vortices might emerge where the red spot once dominated, drawing energy from the surrounding atmosphere and developing into smaller, persistent storms. The nearby jet streams could also change their paths, altering the boundaries that separate Jupiter's immense atmospheric bands. You can imagine the planet's weather as a constantly moving network, where each current influences those around it. Remove one major structure, and the remaining flows must adjust. Jupiter has already shown how dramatically its cloud bands can transform. In 1989 and 2010, the South Equatorial Belt underwent major fading events, becoming difficult to distinguish before eventually returning. Those episodes were temporary. The Great Red Spot would represent something different. Its disappearance would remove a long lived vortex that has occupied the same broad region for generations, leaving no established mechanism for recreating that exact structure. One modeling study suggests the empty region could break into several smaller storms. Instead of a single dominant vortex, Jupiter might develop a scattered family of long lived successors, each occupying part of the circulation that once belonged to the red spot. Another possibility is much less dramatic. The surrounding jet streams could gradually close the gap, allowing the atmospheric bands to reorganize until the former location becomes difficult to distinguish from the surrounding cloud deck. Neither outcome can currently be ruled out. The uncertainty comes from Jupiter itself. We have never watched one of its largest atmospheric structures disappear completely, so there is no historical example that scientists can use as a direct comparison. Even the earlier South Equatorial Belt disruptions provide only limited guidance. A cloud band can fade and return while the deeper circulation remains intact. The red spot reaches far below the visible atmosphere, connecting its behavior to structures that cannot be observed directly from above. That distinction makes prediction especially difficult. A visible change at the cloud tops could spread downward, or deeper circulation might remain largely unaffected while the surface appearance transforms. For you, the eventual disappearance might look deceptively simple through a telescope. A red oval would become smaller, less distinct, and eventually absent from view. Beneath that changing appearance, however, Jupiter's atmosphere would continue moving through enormous interconnected currents. Whether those currents settle into a new pattern within years, develop several replacement storms, or produce changes far beyond the former storm's boundaries remains unknown. For the first time, astronomers are able to watch the possibility approaching through decades of measurements. The red spot's fading therefore offers something rare in planetary science, a chance to observe a giant atmospheric system changing on a human timescale, while the outcome remains genuinely uncertain. Jupiter does not reserve its most powerful weather for one enormous vortex. Across the planet, storms appear, merge, fade, and reform within the shifting bands of its atmosphere, creating a constantly changing population of atmospheric systems. Some are enormous, others are surprisingly compact. Among the most interesting are the white ovals, three storms first observed forming during the 1930s. Over several decades, those vortices gradually moved closer together until they merged into one larger system. By 2000, the merger was complete. The resulting storm became known as Oval BA and later earned another name, Red Spot Jr. Around 2005, its normally pale appearance changed, taking on a reddish color that resembled the Great Red Spot. That transformation gave planetary scientists something remarkably useful. Instead of studying a centuries old mystery alone, they could watch a newer storm undergo a similar change during their own era. Oval BA is considerably smaller than the Great Red Spot, yet it remains a substantial atmospheric vortex. Its interactions with the larger storm have occasionally produced temporary changes in rotation, allowing researchers to observe how neighboring systems exchange momentum when their boundaries approach one another. Jupiter creates other forms of organized weather as well. Brown barges appear within the north equatorial belt, where elongated anticyclonic systems can persist for years before changing shape or disappearing. These storms matter because they reveal something important about Jupiter's atmosphere. Its weather is not organized around one dominant phenomenon. Instead, countless vortices occupy different regions, each responding to the surrounding winds, pressure gradients, temperature differences, and deeper atmospheric circulation. Then there is lightning. Spacecraft observations have shown that Jovian lightning behaves differently from the familiar flashes we see on Earth. Much of it occurs near Jupiter's poles, far from the equatorial region where the Great Red Spot resides. The source appears to be deeper as well. Scientists have linked many of these electrical discharges to water clouds buried within Jupiter's atmosphere, where powerful convection carries material upward and downward through enormous vertical distances. Some detected discharges may release thousands of times more power than the strongest lightning observed on Earth. Imagine watching one of those flashes unfold inside an atmosphere where storms can persist for years. The electrical discharge becomes part of a much larger circulation, connecting deep clouds with movements extending through the surrounding atmosphere. For you, this changes the way Jupiter's storms can be understood. Each vortex is a visible expression of deeper atmospheric motion, shaped by currents that continue far beyond the boundaries we can see. Oval BA offers a natural comparison. Brown barges provide another. Polar lightning adds another layer entirely. Together, they show that Jupiter's atmosphere is filled with interacting systems rather than isolated weather events. The Great Red Spot may be the most recognizable of them all, but its survival depends on the same vast and complicated atmosphere that produces storms of many different sizes, colors, structures, and lifetimes. The Great Red Spot does not end where its visible clouds fade. Above that enormous vortex, charged particles move through Jupiter's powerful magnetic environment, creating electrical activity that reaches beyond the weather we can see. Juno gave scientists another way to study this hidden connection. Its instruments detected radio emissions associated with Jupiter's atmosphere, revealing electrical behavior that cannot be understood from visible light images alone. Radio waves carry information differently. They can escape the cloud layers. Jupiter has been known for decades as a powerful natural radio source. Some of its strongest emissions are connected to interactions between the planet and its volcanic moon, Io, where electrically charged material becomes entangled with Jupiter's magnetic field. The Great Red Spot adds another piece to that picture. Measurements near the storm have shown changes in the surrounding electromagnetic environment, giving researchers clues about how its turbulent atmosphere interacts with charged particles above the clouds. These particles can become accelerated by Jupiter's immense magnetic field. As they move through that environment, their motion can produce electromagnetic radiation across different wavelengths, including radio frequencies that spacecraft can detect. You cannot see this activity with your eyes. Yet the storm leaves an electrical signature. That signature matters because the Great Red Spot occupies a region where enormous atmospheric motions occur inside an exceptionally strong magnetic field. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's field near their respective surfaces, creating an environment unlike anything surrounding a planet in our neighborhood. The storm, therefore, exists inside more than an atmosphere. It is immersed in a vast electromagnetic system that reaches thousands of miles through surrounding space. Every major movement inside the storm can potentially influence that environment. Turbulence can redistribute charged particles. Vertical convection can transport material between atmospheric layers, and interactions near the cloud tops can alter the behavior of particles moving through the magnetic field. But the precise relationship remains difficult to isolate. A radio signal can have several contributing sources, and Jupiter's magnetosphere is constantly active. Distinguishing an emission produced by the storm itself from broader planetary activity requires measurements taken across time, location, frequency, and magnetic conditions. That is why Juno's repeated observations matter. Instead of treating the Great Red Spot as an isolated weather feature, scientists can compare its atmospheric behavior with changes occurring around it. The result is a more complicated picture. The storm has atmospheric motion, thermal structure, chemical layers, electrical activity, and interactions with Jupiter's magnetic environment. These systems overlap, sometimes influencing one another across enormous distances. For you, the visible red oval is only one part of that structure. Much of what defines the storm exists beyond ordinary vision, carried through radiation, magnetic fields, and particles moving above the clouds. The Great Red Spot can therefore be studied in more than one language of physics. Light reveals its color and shape. Microwave observations reveal its depth. Radio measurements provide another trace of activity beyond the visible atmosphere. Together, these signals show a storm whose influence extends farther than its clouds suggest. The stripes across Jupiter are more than patterns on a distant cloud deck. Beneath every bright zone and dark belt, immense currents continue downward, carrying the planet's weather into regions no ordinary telescope can reach. Juno's microwave radiometer allowed scientists to trace these structures at different depths. Instead of seeing only the upper atmosphere, researchers could compare temperatures and compositions beneath the visible clouds, revealing that Jupiter's atmospheric bands continue far deeper than expected. The depth is difficult to picture. The jet streams reach roughly 1,800 miles below the cloud tops. At that depth, pressure rises to around 100,000 times the pressure of Earth's atmosphere at sea level. Hydrogen behaves differently there. Under such crushing conditions, the gas becomes increasingly compressed until its familiar properties begin to change. Farther down, hydrogen enters an extraordinary state called metallic hydrogen, where the pressure becomes great enough for the material to conduct electricity like a metal. This layer matters enormously. Jupiter's powerful magnetic field is believed to originate within its electrically conducting interior, where metallic hydrogen allows enormous electrical currents to flow through the planet. For us, that creates an unusual connection between weather and magnetism. The clouds we see from Earth are linked through deep atmospheric motion to the region where Jupiter's magnetic environment is generated. Juno provided another line of evidence through gravity measurements. As the spacecraft repeatedly passed Jupiter, tiny variations in the planet's gravitational pull revealed differences in the distribution of moving material beneath the clouds. Those measurements were subtle. Their meaning was profound. The gravitational variations were consistent with deep jet streams extending thousands of miles beneath the visible atmosphere. Scientists could therefore test the depth of Jupiter's weather without needing to send a probe into those crushing regions. You can think of the visible bands as the upper expression of something much larger. The cloud tops show where sunlight illuminates Jupiter's atmosphere, while the deeper measurements reveal currents continuing downward through immense layers of compressed hydrogen. This also changes the meaning of the Great Red Spot's surroundings. Its neighboring jet streams are connected to atmospheric structures extending far below the storm itself, so their behavior cannot be understood solely from what happens near the cloud tops. At these depths, pressure and conductivity reshape the physics. Heat moves through the interior, material circulates through the atmosphere, and electrical currents interact with Jupiter's magnetic field. The planet becomes a single connected system. There is no simple boundary separating weather from interior physics. Instead, the transition unfolds gradually, with atmospheric motion reaching downward until hydrogen enters the metallic state beneath it. Juno's measurements gave scientists the first strong indirect evidence that Jupiter's weather reaches this far into the planet. What looks like a layered atmosphere from a distance is therefore part of a much deeper structure, extending from the visible clouds toward the electrically conducting interior. When you look at Jupiter's familiar bands, you are seeing only the uppermost expression of that motion. Beneath them, currents continue through thousands of miles of atmosphere, carrying energy and momentum into a world where even hydrogen has been transformed by pressure. Ammonia should have been one of the easier ingredients to map across Jupiter. Instead, Juno found a planet where this compound gathers, rises, sinks, and shifts with surprising complexity. Microwave measurements revealed strong differences in ammonia concentration between latitudes and depths. In some regions, ammonia-rich air rises from far below the visible clouds, carrying material upward through the atmosphere before spreading into higher layers. The pattern becomes especially striking near Jupiter's equator. There, scientists identified an enormous column enriched with ammonia, extending from deep within the atmosphere toward the cloud tops. Some researchers have informally described this feature as an ammonia river because the material appears to move through the planet in a concentrated vertical pathway. It was an unexpected discovery. Earlier models generally assumed that ammonia would become more evenly distributed at depth. Juno showed something more complicated, with deep circulation transporting the compound through narrow regions instead of mixing it uniformly across the planet. The Great Red Spot adds another layer to that puzzle. Beneath portions of the storm, microwave observations indicate reduced ammonia abundance at certain depths. That depletion suggests the vortex is influencing how ammonia moves through its surroundings, either by drawing material away, redistributing it vertically, or altering the circulation that carries it. We can, therefore, follow the chemistry as part of the weather itself. Ammonia is especially important because it helps form Jupiter's highest visible cloud layer. When ammonia combines with other compounds under the right atmospheric conditions, it contributes to the bright clouds that define much of the planet's appearance. Its movement also affects how energy travels through the atmosphere. Rising ammonia-rich material can transport heat and composition upward, while descending air can return altered material toward deeper regions. That makes the red spot more than a rotating feature surrounded by clouds. If its circulation changes the local abundance of ammonia across thousands of miles, then the storm is modifying the physical properties of the atmosphere around it. The effect reaches beyond what our eyes can see. A visible cloud can reveal where condensation occurs, but microwave observations expose what lies beneath. They allow scientists to trace chemical differences through layers that ordinary cameras cannot distinguish, giving us a deeper view of Jupiter's atmospheric machinery. For the red spot, those measurements suggest a complicated exchange with its neighborhood. Ammonia is being moved through the same immense atmosphere that carries heat, momentum, and electrical activity. You could look at Jupiter's cloud tops and see only color and structure. Beneath those patterns, chemistry is moving too. The ammonia distribution shows that Jupiter's weather has a chemical dimension, with enormous currents carrying material through depths that remain inaccessible to direct sampling. Even within one storm, the atmosphere can separate into distinct chemical regions, revealing a planet whose weather is governed by processes operating far below the level our eyes can reach. On December 7th, 1995, a small atmospheric probe separated from the Galileo spacecraft and began falling into Jupiter. It was the first human-made object designed to enter the planet directly. The descent began at roughly 106,000 miles per hour. Friction and pressure built almost instantly, subjecting the probe to forces reaching 228 times Earth's gravity. Its protective heat shield endured an entry more violent than any spacecraft atmospheric entry recorded at the time. Then the probe deployed its parachute. For 57 minutes, it continued downward while transmitting measurements back to Galileo. Each transmission offered another glimpse into an atmosphere that no telescope could directly sample. Winds remained unexpectedly strong with increasing depth, challenging the assumption that motion would gradually weaken below the visible clouds. The chemistry raised even more questions. Jupiter's atmosphere contained less water than many models had predicted at the probe's location, while several noble gases appeared unexpectedly abundant compared with the composition of the Sunday. That last detail mattered because Jupiter is often treated as a preserved record of the material from which the solar system formed. If its atmospheric composition differs from those expectations, then the planet's history may involve processes more complicated than simple accumulation of primordial gas. Yet, there was a problem hidden inside the success. The probe entered a region later recognized as a Jupiter hotspot, an area with unusually low cloud cover and exceptionally dry conditions. Instead of sampling an average slice of the atmosphere, it may have descended through one of the planet's least representative environments. Imagine trying to understand an entire ocean from a single patch where the water happens to be unusually warm. The measurements can be genuine and precise while still describing an unusual part of the whole. For us, that distinction becomes especially important near the Great Red Spot. Galileo reached only about 95 miles beneath the cloud tops, while the storm's deeper circulation may extend hundreds of miles farther into Jupiter. The probe was already struggling under crushing pressure at that depth. Its final signals arrived after less than an hour of descent, leaving no instrument behind to continue the investigation. Nothing followed it. No second probe has entered Jupiter's atmosphere since Galileo. Modern spacecraft can map the planet remotely, measuring gravity, microwaves, magnetic fields, and atmospheric motion from safer distances. Those observations reveal astonishing depth, but they still cannot replace a physical instrument descending through the layers themselves. A future atmospheric mission could change that, especially if it reached the deeper levels associated with the Great Red Spot. Such a probe would face pressures, temperatures, and atmospheric forces far beyond anything Galileo encountered. For now, Galileo remains our only direct witness from inside Jupiter's atmosphere. Its measurements are invaluable, yet they also carry an unusual limitation. The only place we have ever sampled may have been the place least suited to represent the planet as a whole. On March 5th, 1979, Voyager 1 passed Jupiter at a distance of roughly 174,000 miles. For the first time, humanity could examine the Great Red Spot in genuine detail. The pictures changed its identity. What had appeared through Earth-based telescopes as a broad oval became a complicated structure, threaded with smaller motions and bordered by a distinct boundary. Clouds curled around one another inside the larger vortex, while turbulence gathered along its edges. Voyager also revealed that the red spot shared its neighborhood with other storms. Smaller white ovals moved through nearby atmospheric bands, sometimes passing beneath or around the enormous vortex. Their presence showed that Jupiter's weather was connected across scales, with individual storms exchanging momentum inside a much larger circulation. 4 months later, Voyager 2 arrived for another view. The second encounter gave scientists something precious, a chance to compare the storm after a short interval and search for changes within its internal motion. From those observations came the first detailed velocity maps of the red spot. They confirmed its counterclockwise rotation and showed that different regions moved at different speeds. The outer portions traveled faster, while deeper central regions turned more slowly, revealing that the storm possessed internal dynamics rather than behaving as one rotating body. Voyager was also exploring beyond the famous storm. Its cameras detected Jupiter's faint ring system, a feature previously unknown, and its instruments gathered close observations of the planet's four largest moons. Yet there was a boundary the spacecraft could not cross. Its cameras observed visible and infrared light from above the clouds. Those wavelengths could reveal structures near the upper atmosphere, but they could not penetrate deeply enough to expose what lay underneath. For the scientists studying the images, that limitation mattered. Every swirling feature suggested motion below the visible layer, yet the evidence stopped at the cloud tops. You could see the surface moving. You could not see what powered it. That gap remained for decades. Voyager had shown that the red spot contained structure, variation, and complicated motion. It had established the storm as a physical system worth studying in its own right, while leaving its deeper machinery hidden behind layers of atmosphere. The spacecraft continued outward, carrying its observations away from Jupiter. Back on Earth, researchers returned to those images again and again, measuring shapes, tracking cloud motions, and building increasingly sophisticated models from what could be seen. But the deepest questions remained untouched. How far did the circulation extend? What chemistry existed beneath the visible clouds? Where did the storm draw its energy? And how did the surrounding atmosphere shape its evolution? Voyager could only answer from above. Nearly 4 decades would pass before another spacecraft arrived with instruments capable of probing beneath the visible atmosphere, transforming the red spot from something photographed into something measured at depth. In December 2000, Cassini passed Jupiter on the long journey toward Saturn, turning its instruments toward the giant planet before continuing outward. Unlike earlier flybys, this encounter brought a much richer collection of measurements to the red spot, especially its hidden thermal structure. Cassini's visual and infrared mapping spectrometer examined the storm in wavelengths that revealed differences invisible in ordinary images. Across the cloud tops, temperatures varied from one region to another, allowing scientists to trace patterns of heating and cooling across the vortex. Those variations also helped researchers distinguish the storm's upper structure from the surrounding atmosphere. The red spot appeared colder than the surrounding atmosphere at its upper cloud level. That difference carried an important clue. Rising air expands as pressure falls, and expansion causes cooling, so the thermal pattern was consistent, with material being driven upward by powerful circulation beneath the visible clouds. For us, this adds another dimension to the storm. Shape tells us where clouds move. Temperature can tell us where the atmosphere itself is moving vertically. Cassini also used a technique called radio occultation. In this method, scientists monitor changes in a spacecraft's radio signal as it passes through a planet's atmosphere. Those changes reveal information about atmospheric density and composition at different levels, providing measurements that ordinary imaging cannot supply. The Jupiter campaign became even more valuable because Cassini was not observing alone. The Hubble Space Telescope watched from Earth orbit, ground-based observatories followed the planet, and the Galileo spacecraft continued its own measurements from the Jovian system. Different instruments were seeing different pieces of the same atmosphere. That coordination created an unusually detailed snapshot of the red spot near the beginning of the new millennium. Visible observations traced cloud motion, infrared measurements revealed thermal patterns, and radio techniques supplied information about the atmosphere itself. Together, these observations gave scientists a broader view of how the storm interacted with its surrounding environment. The timing mattered. Jupiter's atmosphere changes continuously, so simultaneous observations allow scientists to separate genuine physical behavior from differences caused by observing the planet at different times. Cassini's measurements, therefore, became a reference point for later investigations. They established a thermal picture against which newer observations could be compared, giving researchers a way to ask whether the storm's behavior had changed over time. When Juno eventually began probing Jupiter from much closer range, some of its measurements did not simply confirm what Cassini had suggested. They exposed deeper structures and temperature relationships that could not be understood from the cloud tops alone. That contrast is important. Science advances through measurements that fit together, but also through observations that refuse to fit neatly. Cassini had shown that the red spot's upper atmosphere possessed a measurable thermal architecture. Its observations also demonstrated how much could be learned when multiple instruments watched the same storm at once. Juno would reveal that the architecture continued far beneath it, connecting the visible storm to circulation operating at depths no previous flyby could examine. Across the outer planets, storms follow different rules, shaped by different interiors, temperatures, and rotations. When we compare Jupiter with its neighbors, the Great Red Spot becomes part of a much larger planetary experiment. Saturn offers the most recognizable contrast. Near its north pole, a six-sided jet stream surrounds a central vortex that has persisted since the Voyager era. The pattern stretches roughly 1,250 miles across, yet its geometry is fundamentally different from Jupiter's Great Storm. Saturn's feature is a polar cyclone, while Jupiter's is an anticyclone embedded between opposing atmospheric bands. That distinction matters. Location changes the physics. At Saturn's pole, the storm follows the planet's rotational environment in a region where sunlight is weak and seasonal cycles are extreme. The six-sided boundary appears to emerge from interactions between fast-moving atmospheric currents, producing a shape that remains remarkably stable over long periods. Neptune gives us another comparison. When Voyager 2 passed the distant blue planet in 1989, its cameras revealed a vast feature called the Great Dark Spot. Like Jupiter's storm, it was an anticyclonic system, rotating within the atmosphere and stretching across an enormous region. Then something unexpected happened. The storm disappeared. When the Hubble Space Telescope observed Neptune in 1994, the original Great Dark Spot was gone. A different dark storm had appeared elsewhere, this time in the northern hemisphere. Neptune had rearranged its atmosphere within only a few years. For you, this comparison offers a useful distinction. A storm can vanish without the planet losing its ability to create storms. The atmosphere itself remains active, producing new structures as old ones dissolve. Neptune's storms also appear to have shorter lifetimes than Jupiter's Great Red Spot. One possible reason lies beneath the clouds. Neptune releases internal heat, but its energy supply and atmospheric structure differ greatly from Jupiter's, changing how deep circulation can sustain long-lived disturbances. Uranus presents an even stranger case. Its atmosphere generally appears less dominated by enormous persistent storms, despite the planet possessing powerful winds and occasional bursts of activity. Its extreme axial tilt changes how sunlight is distributed across the seasons, producing a very different thermal environment from Jupiter's. Now the four gas giants begin to look less like variations of one world. Each combines rotation, atmospheric depth, internal heat, and solar energy differently. That combination may determine whether a storm survives for years, decades, or centuries. Jupiter occupies an unusual position within this comparison. Its rapid rotation organizes powerful jet streams, its enormous atmosphere extends deep into the planet, and heat, rising from its interior, continues to drive convection beneath the visible clouds. Those ingredients create an environment where disturbances can become remarkably persistent. Saturn can build extraordinary atmospheric structures. Neptune can produce storms that appear and disappear. Uranus can remain comparatively restrained. Jupiter does something different. Its atmosphere can take a storm and keep it alive for generations. A storm on Jupiter can teach us about a world we have never seen. That connection becomes especially important when we turn our attention toward planets orbiting other stars. Thousands of exoplanets have now been confirmed, including many gas giants with atmospheres shaped by intense radiation and rapid circulation. Among them are hot Jupiters, enormous worlds orbiting so close to their stars that their atmospheric conditions can differ radically from anything found around our Sunday. Yet when scientists model those distant atmospheres, they still need somewhere to begin. Jupiter provides that foundation. The Great Red Spot gives us a natural laboratory for studying how enormous storms form, move, exchange energy, and eventually change. Juno's measurements revealed that Jupiter's visible weather reaches at least 1,800 miles beneath the cloud tops, showing that atmospheric circulation can penetrate far deeper than earlier models assumed. That discovery reaches beyond Jupiter. If deep circulation governs gas giants throughout the galaxy, then atmospheric models for distant planets may need much greater vertical depth. A storm detected on another world could be connected to processes occurring hundreds or thousands of miles beneath the clouds. We would never see those depths directly. Instead, we would search for their effects. Temperature patterns can reveal where energy is moving. Chemical abundances can show where material rises from deeper layers. Changes in atmospheric brightness can expose shifting cloud structures, even when the storm itself cannot be resolved. For distant worlds, those clues may be the only evidence available. The Nancy Grace Roman Space Telescope, planned for launch in the late 2020s, will expand our ability to study planets and their environments through large astronomical surveys. Other future observatories will push atmospheric measurements further, searching for chemical and thermal signatures across worlds separated from us by vast distances. A great red spot somewhere else might never appear as a recognizable oval. Its presence could instead emerge through an unusual temperature pattern, an unexpected chemical imbalance, or periodic changes in the planet's reflected light. That possibility changes how we think about planetary weather. You might look at a distant gas giant and see only a point of light. Hidden within that tiny signal could be an atmosphere containing storms larger than Earth, driven by circulation extending deep into the planet. The physics would still be operating. Understanding Jupiter, therefore, gives us a reference point for interpreting those faint signatures. If we learn why its great storm survived for centuries and why its structure is now changing, we gain a way to test whether similar atmospheric systems can persist elsewhere. But there is an important limit. Jupiter remains the only gas giant whose atmosphere we have explored with spacecraft instruments at close range and sampled directly. Every distant atmosphere must be interpreted through models, and every model carries assumptions inherited from what Jupiter has taught us. The Great Red Spot is therefore more than one storm on one planet. It is part of the framework we use to understand weather across an entire class of worlds. A spacecraft can spend years gathering answers, yet its final contribution may arrive long after its last transmission. That is part of the strange legacy of Juno, because the measurements it collected continue to reshape how scientists understand Jupiter. Juno's prime mission was extended in 2021, adding 42 orbits and transforming the spacecraft into a broader explorer of Jupiter, its rings, and several major moons. The extension brought close encounters with Ganymede, Europa, and Io, while allowing repeated observations of atmospheric structures that could never be understood from one passing glimpse. Repeated passes changed the science. Each encounter gave researchers another measurement of the same planet under slightly different conditions. For the Great Red Spot, that meant watching its dimensions, cloud structures, surrounding flows, and internal patterns evolve rather than treating one observation as a permanent snapshot. That distinction matters. A single image can reveal structure. Time reveals behavior. Juno's microwave instruments also continued probing beneath the visible clouds, helping refine our understanding of how Jupiter's atmosphere changes with depth. The spacecraft's gravity measurements added another layer, allowing scientists to connect visible atmospheric patterns with enormous currents extending deep into the planet. Some discoveries came from features far removed from the red spot itself. Juno detected waves moving through Jupiter's dense atmosphere, patterns that resemble internal waves in Earth's oceans. These disturbances can transport energy and momentum through the atmosphere, potentially influencing larger weather systems as they travel. We are still learning how those waves interact with Jupiter's major storms. The mission also transformed our knowledge of Jupiter's moons. Close encounters with Ganymede revealed details of its surface and magnetic environment, while repeated passes over Io provided unprecedented views of its volcanic activity. Europa received close attention as well, with measurements designed to improve our understanding of its icy exterior and surrounding environment. Yet the mission itself has now reached the end of its planned operational journey. NASA's approved extended mission ran through September 2025, and Juno's trajectory was designed to end with the spacecraft entering Jupiter's atmosphere. That ending carries a practical purpose. Juno's changing orbit meant it no longer threatened to collide with Europa or other potentially habitable worlds. Instead, Jupiter became both the destination and the final resting place for the machine that spent years studying it. But the scientific work does not disappear with the spacecraft. Juno returned more than 3 terabits of scientific information during its mission, and researchers continue examining observations collected years earlier. New analyses can combine old measurements with improved models, revealing patterns that were difficult to recognize when the data first arrived. For us, that creates an unusual kind of exploration. The spacecraft may be gone, but its measurements remain active in laboratories around the world, continuing to change what we think Jupiter is. For generations, the Great Red Spot has existed as a fixed point in human attention, even while everything around it changed. Kingdoms disappeared, borders shifted, and generations passed beneath changing skies, yet observers kept returning to the same distant planet. Giovanni Cassini recorded a large dark feature on Jupiter in 1665, and later observations described similar markings near the same latitude. Whether those early sightings represent the modern storm itself remains uncertain, because Jupiter's atmosphere can produce temporary features that resemble one another. Still, the records establish something remarkable. Humans were already noticing Jupiter's changing weather more than 3 centuries ago. By the 19th century, telescopes had improved enough for astronomers to document the Great Red Spot systematically. Observers could compare its color, position, dimensions, and internal structure across different years, creating a record that became increasingly valuable as the storm slowly changed. Much of that history came from amateurs. Across Europe and elsewhere, dedicated observers spent nights at their telescopes, recording what professional observatories could not monitor continuously. The British Astronomical Association helped organize observations, while individual astronomers contributed drawings, measurements, and photographs that extended the historical record across decades. Their work matters because Jupiter does not wait for convenient observing schedules. Weather on the planet changes while observatories sleep. Amateur astronomers, spread across different longitudes, could sometimes fill those gaps, preserving details that might otherwise have vanished between major observing campaigns. Modern citizen science continues that tradition, with carefully calibrated images allowing researchers to measure changes in the storm's color, shape, and surrounding atmosphere. When you place those observations together, the red spot becomes more than a target in a telescope. It becomes a record, assembled by thousands of separate nights across different countries, instruments, and generations. Its changing size is especially revealing. Measurements from the 19th century show a storm considerably larger than the one we observe today, while later observations trace a long decline in its dimensions. The exact rate has varied, and historical measurements contain uncertainties, but the overall trend survives comparison across independent observers and technologies. That makes the history unusually personal for planetary science. The storm sits hundreds of millions of miles away, yet its changing appearance has been documented by people standing beneath ordinary night skies. Some used large observatory instruments. Others watched through modest telescopes from backyards and rooftops. Their observations crossed generations. A person who first recorded the storm could never have known the spacecraft that would eventually pass above it. They could not have imagined microwave instruments probing beneath its clouds, or gravity measurements revealing motion deep inside Jupiter. Still, they added another observation, then another. The red spot has therefore lived through more than changing scientific theories. It has lived through changing observers, changing instruments, and changing civilizations, while remaining one of the few planetary features humans have watched for centuries. Now, the record carries a new kind of evidence. For the first time, our long history of watching Jupiter includes sustained measurements of a storm whose dimensions are declining. There is a boundary to what observation can reveal, and Jupiter keeps that boundary deeper than our instruments can reach. Juno transformed our view of the Great Red Spot, yet some of its most important questions remain unresolved. We still do not know exactly why the storm is shrinking. Several mechanisms have been proposed, involving surrounding turbulence, smaller vortices, and changes in the energy exchanged with Jupiter's atmosphere. None explains the observed contraction completely, especially its changing rate over recent decades. The storm is changing, but the precise cause remains unsettled. Different measurements capture different stages of that decline, making the timeline itself an important part of the mystery. Deeper inside, another uncertainty waits. Juno's microwave measurements trace the storm's route to roughly 300 miles below the visible clouds, yet that depth is not a hard floor. Beyond the instrument's strongest sensitivity, scientists must rely on indirect evidence and models. We can infer structure from the measurements, but we cannot simply look deeper. Then there is the color itself. The Great Red Spot contains complex atmospheric chemistry, including compounds called chromophores, which absorb certain wavelengths of sunlight and leave the clouds appearing reddish. We know these materials are involved, but the complete chemical pathway that produces them, preserves them, and distributes them through the storm remains under investigation. Even the storm's future is uncertain. It might settle into a smaller, stable vortex as its surrounding environment changes. It might continue losing energy until the circulation becomes too weak to maintain its organized structure. Both possibilities remain compatible with current observations. What would Jupiter look like without it? That question reaches beyond the storm itself. The Great Red Spot exchanges energy and momentum with neighboring atmospheric currents, so its disappearance could alter circulation around the latitude where it has persisted. Exactly how those changes would unfold is difficult to predict because Jupiter's atmosphere is a deeply connected system. There is another possibility we cannot test. The Great Red Spot may not be unique in Jupiter's history. Earlier anticyclones could have formed, evolved, and disappeared long before telescopes existed. Any evidence they left may now be buried within atmospheric layers that no spacecraft has directly sampled. And this uncertainty extends beyond Jupiter. If enormous, long-lived vortices can arise from a particular combination of rotation, internal heat, atmospheric depth, and chemistry, we still do not know how often nature creates that combination elsewhere. Distant gas giants may host storms larger, stranger, or longer lived than anything we have observed. yet their atmospheres remain mostly unresolved. For you and me, the unanswered questions are part of the measurement itself. Every new observation narrows the possibilities, while revealing another layer we cannot yet explain. Jupiter has given us an extraordinary amount of information, but the deepest parts of its weather remain beyond our reach. A storm can become part of human history without ever belonging to us. The Great Red Spot has occupied Jupiter for generations, becoming so familiar that its presence can feel less like an event and more like part of the planet itself. Every astronomer who encountered Jupiter inherited the same feature. Giovanni Cassini recorded a large marking in 1665, while later observers watched the red spot change through increasingly capable telescopes. Photographs from the 19th century preserved its evolving shape, and spacecraft eventually transformed those distant observations into detailed views of its swirling atmosphere. For much of that history, the storm seemed dependable. You could point a telescope toward Jupiter and expect to find it there. Textbooks illustrated it, planetariums displayed it. Generations learned the appearance of Jupiter through that enormous reddish oval, even though the feature itself was always moving, changing, and exchanging energy with the atmosphere around it. That familiarity creates an unusual relationship between observation and time. A human lifetime is short enough to make centuries feel immense. Jupiter's storm has existed across enough generations that its apparent permanence became part of our mental picture of the solar system. Yet, the measurements collected during recent decades have changed that picture. The storm is shrinking. Its dimensions have declined substantially compared with historical measurements, and observations from spacecraft have revealed changes within its structure that earlier generations could not detect. We now know the red spot has a finite physical state, shaped by atmospheric circulation, surrounding vortices, energy exchange, and conditions deep beneath its clouds. Eventually, that state may change again. Whether the storm settles into a smaller configuration or eventually disappears remains uncertain. The timescale could extend for many decades or longer, and scientists cannot yet predict its final evolution with confidence. Still, the possibility of an ending changes how we understand every historical image that came before. Those old photographs become more than records of appearance. They become timestamps in the life of a planetary system. A photograph from the 19th century captures a storm larger than the one observed today. A spacecraft image from the 20th century records another stage. Juno then adds measurements from beneath the clouds, revealing that the visible feature is connected to atmospheric processes extending far deeper than anyone could see with a telescope from Earth. The storm we know is therefore one moment in a much longer process. If it eventually disappears, another vortex might someday form somewhere else on Jupiter. It could become enormous. It could persist for centuries, but it would have no connection to the generations of observers who watched the red spot cross Jupiter's face. You would be looking at a new storm, and that distinction reaches beyond Jupiter. The cosmos contains structures that appear permanent only because our lives are too brief to witness their full histories. Stars are born and die. Worlds change their surfaces. Atmospheres reorganize. Even planetary systems evolve. The Great Red Spot simply gives us an unusually visible example. For centuries, humanity watched the same storm and gradually mistook persistence for permanence. Now, the observations are teaching us something more precise. A thing can endure for hundreds of years and still be temporary. Even Jupiter's most familiar feature has a history, and histories have endings. Seen from Earth, the Great Red Spot can appear almost self-contained, a colored mark against Jupiter's brighter atmosphere. Yet its present width remains greater than the diameter of Earth, giving us a scale that is difficult to hold in the mind. Imagine placing our entire planet inside the storm. Every ocean would fit, every continent would fit. The mountain ranges, cities, forests, and people would all occupy a space smaller than this single atmospheric vortex. There would still be room beyond the edges, beneath the surrounding clouds of Jupiter. And yet, within Jupiter, the red spot is only a regional feature. That distinction becomes harder to grasp when we widen the view. Jupiter contains roughly 1,300 Earths by volume, making the planet itself vastly larger than the world beneath our feet. The storm that can encompass Earth therefore occupies only a portion of an enormous atmosphere. Even Jupiter is not the upper limit. Astronomers have discovered gas giant planets around other stars with masses many times greater than Jupiter. Some of these worlds belong to a class called hot Jupiters, massive planets orbiting extremely close to their stars, where intense radiation can reshape their atmospheres and drive weather unlike anything found in our solar system. The numbers become increasingly difficult to picture. Human intuition evolved around distances measured by footsteps, roads, mountains, and horizons. Our brains are remarkably capable at navigating those scales, yet planetary dimensions have no natural equivalent in everyday experience. We can understand the measurements intellectually without ever developing a complete physical sense of what they represent. So we build instruments. We send spacecraft across the solar system and place them thousands of miles above distant worlds. We construct microwave radiometers capable of detecting thermal and chemical information beneath cloud layers that ordinary cameras cannot penetrate. Juno brought those instruments within roughly 2,600 miles of Jupiter's cloud tops. From that distance, measurements could probe structures extending far beneath the visible atmosphere, transforming a familiar oval into a system with enormous depth. The deeper measurements change the scale again. The red spot's circulation reaches roughly 300 miles beneath the cloud tops, while Jupiter's broader atmospheric jets extend more than 1,800 miles downward. Far below the levels visible from Earth, hydrogen enters conditions where it can become electrically conductive metallic hydrogen. We began by looking at a storm, then the storm revealed a planet, and the planet revealed an interior whose physical behavior reaches beyond ordinary terrestrial experience. Each improvement in our measurements has expanded the dimensions of the system we thought we understood. There is something practical in that lesson. When you cannot experience a scale directly, measurement becomes our bridge to it. Numbers give shape to distances our senses cannot cross, while spacecraft turn those measurements into observations from places no human could reach. The Great Red Spot is therefore more than something enormous. It is a reminder that size itself can hide complexity. A storm larger than Earth can still be only one feature of Jupiter. Jupiter can dominate our solar system while remaining ordinary beside larger worlds around other stars. And those worlds may themselves be small pieces of systems we have barely begun to understand. The farther we look, the larger the frame becomes. Juno found something inside the Great Red Spot that is difficult to photograph. It is a pattern hidden beneath the visible colors, where the atmosphere behaves as a deep and organized system. Microwave radiometry gave scientists access to layers that ordinary cameras could never reach. Measurements of ammonia, temperature, and electrical properties revealed variations extending far below the cloud tops. Each signal added to the storm's internal architecture. What emerged was structure where simplicity had once seemed sufficient. The Great Red Spot reaches roughly 300 miles beneath the visible atmosphere, with different layers responding to pressure, chemistry, heat, and motion in their own ways. Its circulation is connected to an environment extending deep into Jupiter, a planet without a solid surface beneath the clouds. That changes the meaning of the word storm. On Earth, we picture weather as something occurring above solid ground within a relatively thin atmosphere. Jupiter offers no such boundary. Its atmosphere gradually becomes denser and more extreme, with hydrogen compressed until it behaves in unfamiliar ways. The red spot exists inside that continuum. You can trace its visible shape from distant telescopes, then follow the measurements downward, layer after layer, until the familiar oval becomes part of a much larger physical system. The deeper we measure, the less useful it becomes to imagine the storm as a simple feature painted onto Jupiter. Juno's instruments were built on Earth by scientists working with incomplete information about what they would eventually encounter. They could study Jupiter from immense distances, but they could not directly sample the atmosphere before the spacecraft arrived. Then Juno came within roughly 2,600 miles of the cloud tops. From there, its instruments transformed distant observation into direct measurement. Microwave signals carried information from depths that visible light could not penetrate, while other instruments recorded gravity, magnetic fields, particles, and radiation around the planet. Together, those measurements changed the question. We were no longer asking only what the Great Red Spot looked like. We were asking how its layers interact, where its energy moves, how its chemistry changes with depth, and why the entire structure has remained coherent for so long. There is something larger in that discovery. The universe rarely gives us a complete picture on the first attempt. We observe a surface, build an explanation, test it against new evidence, then discover that reality contains another layer beneath the one we understood. The Great Red Spot became a remarkable example of that process. For centuries, we watched its uppermost appearance from afar. Modern instruments finally allowed us to measure what existed below. The result was deeper, more complicated, and more dynamic than the visible storm suggested. That is what was found inside. Not an empty depth beneath a colored cloud, but a physical system with layers, currents, chemistry, heat, and electrical behavior interacting across enormous distances. And the lesson reaches beyond Jupiter. Whenever we look more carefully at something familiar, the universe gives us another reason to keep looking. If the Great Red Spot eventually disappears, something unprecedented will leave Jupiter with it. For centuries, the storm has occupied a place unlike any other known weather system in our solar system. No other observed planet has given us a vortex with this combination of size, longevity, and persistence. Its ending, if it comes, will probably resist any dramatic moment. There will be no final flash, no sudden collapse. Instead, we would expect a gradual change in the circulation that maintains it. The oval may continue contracting, its winds may reorganize, and the boundary separating the storm from surrounding currents may become less distinct. Generations could pass before the change becomes unmistakable. Imagine an astronomer decades from now examining Jupiter with instruments we cannot yet predict. The planet will still dominate the observation, its bands and storms continuing their enormous circulation. But somewhere within those patterns, one familiar feature may be absent. They will have the records. Voyager images will preserve the storm as it appeared during the early age of planetary exploration. Observations from the Hubble Space Telescope will show how its color and dimensions changed across decades. Juno's measurements will preserve information from layers hidden beneath the visible clouds. Those records will become more than historical images. They will form a scientific memory of a planetary system that no longer exists in the same form. Future researchers could compare their observations with measurements made by people they will never meet, following changes across generations rather than individual lifetimes. You and I experience weather in days, seasons, and years. Jupiter operates on another scale entirely. Its atmosphere can preserve enormous structures long enough for human civilizations to rise, change, and disappear while the same circulation continues above the clouds. That difference gives the storm's ending an unusual character. We are not watching something vanish from one moment to another. We are witnessing a process that stretches beyond any single human life, while our instruments make each stage measurable. Perhaps the most remarkable part is where our generation entered the story. Earlier observers could measure the storm's changing appearance. Spacecraft eventually revealed its surrounding environment. Juno then allowed scientists to investigate its deeper structure, showing that the visible feature was connected to atmospheric layers extending hundreds of miles below the clouds. For the first time, we could study the storm as a three-dimensional physical system rather than only as a shape. That knowledge will remain, even if the storm does not. A future Jupiter may look different from the one we inherited. The atmosphere will continue moving, new vortices may form, and other structures may emerge from the same immense circulation. But the Great Red Spot will have a permanent place in the scientific record. We were here while it changed. We measured it, photographed it, mapped it, and finally looked beneath its surface. And for a brief interval in the history of Jupiter, human beings were able to witness an ancient storm slowly becoming something else. Jupiter asks nothing of us. That may be the most important thing about studying it. For thousands of years, the planet has crossed our sky without needing to explain itself. Ancient observers tracked its movement. Galileo used its moons to challenge the old picture of the heavens, and later generations sent machines across the darkness to approach it. Each step changed what Jupiter meant to us. A distant point of light became a world, then a system of worlds, then an atmosphere whose behavior reached far beneath anything visible from Earth. The pattern matters. Whenever we have built a better way to observe Jupiter, the planet has answered with something unexpected. Telescopes revealed changing bands and spots. Spacecraft measured magnetic fields and radiation. Cameras showed storms in motion. Juno's microwave radiometer allowed us to examine layers hidden beneath the visible clouds. That instrument exists because someone first asked a simple question: what lies underneath? The answer required patience measured in decades. Engineers had to develop sensors capable of operating near one of the harshest environments in the solar system, while scientists had to decide which signals might reveal the atmosphere's deeper structure. Then the spacecraft arrived. Juno did not change Jupiter. It changed our ability to measure it. That distinction reaches beyond this planet. Curiosity begins with an observation, often something so familiar that we barely notice it. A moving point of light, a colored band, a storm that refuses to disappear. Then comes the difficult part. We build the tool. Sometimes that takes years, sometimes generations. The resulting discovery may challenge ideas that seemed reasonable for a long time, forcing us to rebuild the picture with better evidence. Jupiter rewards that process because its scale leaves room for mysteries that cannot be exhausted in one mission. Its atmosphere extends through pressures and temperatures that have no direct counterpart on Earth, while its interior contains hydrogen compressed into exotic states, including metallic hydrogen that conducts electricity. We can measure some of this from orbit. Much remains beyond direct reach. The Great Red Spot itself is changing, and eventually Juno will complete its own journey. The spacecraft will be directed into Jupiter's atmosphere, where its mission will end in the same world it spent years observing. Yet the planet will continue. Its rotation will carry the atmosphere through another day, another season, another century. New vortices will form, existing structures will change. Future spacecraft may carry instruments designed to answer questions we have not yet learned to ask. That is why Jupiter does not need to give us a final answer. It gives us a place to practice looking deeper. You can follow that chain through centuries of observation. Someone notices, someone wonders, someone builds, someone measures, someone discovers that the explanation was incomplete. Then we begin again. Jupiter will outlast every instrument we send there, and probably every theory we build about it. Its immense atmosphere will keep moving, whether we understand it or not. The choice to look belongs entirely to us. And perhaps that is what Jupiter has been asking all along. How far are we willing to go to understand something that never needed us to understand it? When you look toward Jupiter, you are looking backward in time. The light entering your eyes has traveled across space for many minutes before reaching you. Depending on where Earth and Jupiter are in their orbits, that journey takes roughly 35 to 52 minutes. So if you watch Jupiter tonight, you are seeing an earlier Jupiter. The distinction is easy to overlook. Our eyes make distant worlds appear immediate, almost as though we could simply reach across the darkness and observe them directly. But every photon carries a history. By the time it arrives, the event that produced it has already happened. The same principle follows us everywhere. The moon appears roughly 1 1/3 seconds in the past. Sunlight reaches Earth after about 8 minutes. Light from the nearest star takes more than 4 years to arrive. Distance turns observation into archaeology. We do not receive the universe as it happens. We receive traces of what happened before, preserved in light, radio signals, magnetic measurements, and other forms of radiation. For Jupiter, that delay is long enough to matter. A storm can change while its previous image is still traveling toward us. The Great Red Spot may alter its shape, its winds, or its surrounding circulation, yet the evidence of those changes remains somewhere between Jupiter and Earth. You can see the contradiction. We are observing something that is already different. Every spacecraft encounter carries the same limitation. Voyager photographed Jupiter decades ago, but those images remain records of an earlier atmosphere. Juno measures the planet much closer, yet even its signals require time to cross the distance between spacecraft and Earth. There is no instantaneous window into Jupiter. There is only information arriving from different moments. That makes the Great Red Spot a remarkable kind of historical object. The storm itself exists in the present, but every measurement we possess describes a previous state of it. Some observations are minutes old, others are decades old. Still others preserve atmospheric changes that began centuries before anyone recorded them. And yet, together, those observations form an increasingly detailed picture. The images from Voyager revealed structures that earlier telescopes could not resolve. Later observations tracked changes across decades. Juno added measurements from beneath the visible clouds, allowing scientists to reconstruct parts of the storm's deeper architecture. Each generation, therefore, inherits an older picture and adds another layer. What we call knowledge is assembled from these delayed fragments. Tonight, if you look toward Jupiter, The light arriving at your eyes began its journey long before you noticed it. The storm you see has already moved through another stretch of its enormous life. By the time its next signal reaches us, Jupiter will have changed again. That is true across the universe. We never receive the present directly. We receive evidence, carried across unimaginable distances, and build our understanding from what finally arrives. The Great Red Spot is already history when we see it, but history can still be measured. And sometimes, across millions of miles of darkness, an ancient message arrives, carrying enough detail for us to understand something that began changing long before we were here. So, when you close your eyes, tonight, Jupiter will continue turning beyond the darkness, its atmosphere moving through depths we are still learning to understand. And somewhere between that distant world and you, its next message will already be on its way.